Hello everyone and welcome back to another mini concept, this time on chemistry. So today we're going to start with the first law of thermodynamics, particularly about internal energy of a system. And yeah, so we're going to cover everything from what a closed, open, and isolated system is to understanding what the first law means and overall finding a way to quantify it, which is through internal energy. So first, let's try to understand what a system is. Okay, so let's imagine these as different systems. And okay, don't mind the sizes, I'm just bad at drawing. Okay, now you can easily find a distinction between the three, or there's one that is the most distinct from the three, and it's this one right here on the very left. This is what we call an open system. Because if you would imagine that this had a lid, it's open. So basically, heat, energy, matter, they can enter the system as it pleases. So for example, let's say that this were an empty hollow box and it had a lid off. That means that air could flow inside it, like air that originally wasn't inside the box. Or if it were a glass, I could pour more water into the glass because it's an open system. So basically, an open system is a system where more matter can be added, more energy can be added. But it's important to know that when we say added, it means physically there is more energy added into the system, not created, simply added. Now, this is what we call the second one is what we call a closed system. It's literally just the same as the first one, however, this time has a lid. And what happens here? Basically, we don't allow matter to go in anymore. So if this were air, like let's say that this was oxygen, oxygen can't make its way inside it. However, energy can still go inside. It can be transferred using work, or it can be transferred using heat. So heat is in the symbol Q, small q, and but in some references it's also big Q. And work is just W. Right? And in a closed system, energy can still be transferred. However, the matter can't be added. So essentially we're literally talking about the flow of energy in a closed system. Now, how about an isolated system? Oh, well, I just said it. This is an isolated system. And okay, it kind of doesn't look any different, right? But essentially let's just I'll make like a smaller box in here. There. One example of this would be your hydro flask or your thermos. Basically, an isolated system is a closed system separated from like the outside world. So in your aqua flask or your thermos, you have the spot where all of your water is, right? So this is your water, and then you want it to remain hot. Now the way that it remains hot is that between the wall of the place where your water is, it's actually a vacuum. So this is, hold on, this here, there's nothing here. It's just a vacuum, or at least it tries to be a vacuum. Now obviously, the better the aqua flask or thermos is made, the more effective this vacuum is, and that's how you keep whatever water, soup, or food you have warm or cold depending on what you put. And this is an isolated system because we don't allow heat to enter from the outside, so there is no more Q going in, and there is no more work. So basically, in your thermos, no matter how much I push on the wall of your thermos, there's not going to be any change in the energy of your water, because the water exists completely separate from the thermos itself because it's an isolated system. Now, why is this important? So I'm going to remove everything here except for the closed system, because the closed system is essentially what we tend to have. the first law of thermodynamics says that you can't create energy and you can't destroy it. So essentially, everything that happens to a closed system is not going to be new. It's going to be added or it's going to be removed. Let's say that this box contains let's say this box is full of water. Right? Let's say this box is full of water and it has I don't know, let's say that it has 500 joules of energy. Now, let's first understand that this 500 joules of energy, this is what the water inside possesses, right? So, hold on, let's put some water here, put some context. So, the water possesses 500 joules of energy and it can be affected by the surroundings. So, everything around the system, so everything here, this is what we call the surroundings, right? And we're going to simulate, for example, a temperature difference. So, let's say that this high energy, let's say that this is high energy and we're going to put this high energy or high temperature water inside an ice bath. Like this system, we're going to put it inside an ice bath. Think of perhaps a plastic bottle that is filled with hot water and you're going to put it in an ice bath. So the system is still closed, but there can be energy transfer because of the difference in temperature. And the difference in temperature is actually what we call heat. So that is heat, right? And heat is energy transfer or the change in energy because of due to temperature difference. So basically it's thermal energy change. So now we have to wonder, from a hot amount of a hot set of water, we put it inside a cold set of water. We have to determine that will we lose energy from inside the system or will we gain energy from inside the system. And well, typically, right, our hot water would end up cold. So we can say that the system loses heat. So the change would be negative. And this arrow would actually be going to the left. Because energy is flowing outward. Right? And that's important to note because essentially that is how we quantify Q here in this equation. Delta E is equal to Q plus W. So that's step one in understanding that equation, even though I haven't formally introduced it yet, right? And this equation here is our internal energy equation. Now, why did we start with heat? Well, simply put, it's because sometimes we don't really have work done on a system. So, for example, in the case of the water bottle with hot water being put inside cold water, we don't necessarily touch the bottle. We don't necessarily squeeze or expand the bottle ourselves, at least. Instead, it's a repercussion or it's a result of the movement of heat. So think about, for example, let's think about, okay, when objects get cold, they tend to contract, right? And when objects contract, that means that there's a force pushing them inward. So this will lose energy, but then the bottle itself will contract. So this one will have positive work done onto the bottle. And that's the two-edged side of understanding heat and work, because their dynamic isn't exactly always the same. So now let's try to properly quantify the situation. Oh wait, but before that, let's put our short definition of what work is. Work is change in energy due to the application of work. Well, the application of no, let's just say the transfer of energy to a system. Okay, there. So let's just shrink this. It's going to be our little definition over here on the side. Okay, now I'm gonna remove this because we know that this is a closed system. Okay, so questions involving the first law are quite simple, really, and some of them could look like this. Imagine that this 500 joule box or 500 joule system, let's remove the water. This 500 joule system has work done on it, and its work done is equivalent to the work done towards the box is equivalent to 200 joules. So the work done is 200 joules. And it also loses heat, which is equivalent to, let's say, around 100 joules. Okay, so the first thing to do in these questions for internal energy, we have to determine the signs. So we said that work was done on the system. Now, if we're going to do work on the system, we're transferring energy to the system. So work done on is a positive sign. Now, we're going to also take into account the heat. So the heat was lost by the system, right? So the heat is lost. Now, heat is energy, right? And we can say that because it got lost, the system had a negative 100 joules heat, because the heat or the change in the heat would be equal to negative 100 joules since we lose that 100, right? So now we can do a bit of a diagram with this new information. So first, let's start with the work. So we have our work being applied here, and the work done is 200 joules. So 200 joules, and this is a plus. Now we also have our heat, which is lost. So our heat is also going out this way. So this is negative 100 joules. Now all I have to do is just plug into the equation. So our delta E would be equal to negative 100 plus 200. And this is going to be equal to 100 joules positive. Now this is delta E. So what does that mean? That means that the final energy is higher than the original by 100 joules. So what's the final energy of our box? The final energy of our box would thus be 100 plus its original energy. So the energy of the box would be equal to 500 joules plus 100 joules. This is 600 joules. Now, this is obeying the first law, because although we gained the energy, it was transferred from the surroundings. Unless you're God, to quote the organic chemistry tutor, unless you're an omnipotent being, you can't just say that you're going to add energy to a system. So I can't just say that, oh, my 500 joule box gains 100 plus 100 joules of energy. I can't just say that. It has to come from the surroundings, or it has to be explained by the flow of heat and all of that. So that's pretty much it. This one example wraps up the entire first law of thermodynamics. Now, there's also just one more case that may pop up in your exams, and we're going to talk about the cases of gases. Okay, I'm gonna remove this quickly. So we'll keep the 500 joule box. Okay. Now, work is also describable using a different formula. So in physics, we know that work is equal to force times distance. And in gases, we don't exactly know the force done by the gas, but instead we quantify force of a gas in terms of pressure. And pressure is equal to force over area, right? So hold on. Let me show you guys a derivation for this in an intuitive manner. So we don't really know the force of each atom of a gas, right? So we can't quantify it just like how we would a box's force on the ground in terms of its weight and etc. So for a gas, the work done would be equal no, not the work, the force of a gas would be equal to the excuse me, the pressure times the area. This is because pressure is equal to force over area, right? The force divided by the area that it's being done on. So this is the formula for force. Now, we want to get also in work, right? We want to achieve the standard work is equal to force times distance, right? The force times distance. And now in let's say we have a piston or a how to describe, like a 3D container. It doesn't have to be a box, it can be a cylinder, it can be whatever. Now, regardless of whether or not it's going to be vertical or horizontal, there's a third dimension that the air would be traveling to, and the compression is going to be in a certain direction in that third dimension. So we would add another value here, and this other value of distance in the third dimension, we can put z. This would make us have an how to describe, we would end up having a length times width times height. So this length times width is our area, and this is the d. So essentially now we have volume, and this is equal to volume. So now our formula for work done would thus be, hold on, let's remove this. Our formula for work done would end up being the pressure times volume. And this is the formula for work. Now, this is negative, however, because it's somewhat related to the explanation for how work is equal to the negative potential energy. There. So that's in physics. But anyway, this is our formula for work involving gases. Now, how does this come into play? Well, basically, in some examples or some exams, they're going to give you the similar stuff. So let's say that they're going to give us so from the surroundings, from a 500 joule closed system, it loses 100 joules of energy, right? It loses, so it's a minus sign. And the gases inside of the box are compressed. Let's say the gases are compressed from the volume was, let's say, from 1 liter to 0.5 liters under a constant pressure of, say, 2 atmospheres. Okay, so let's just write down that given. So from the volume initial, oh sorry, I forgot to put this volume here is delta. So the change in volume. Because we need to see the work done total, right? Okay, so the initial volume was 1 liter, and the final volume was 0.5 liters. and the pressure is constant at 2 atmospheres. Okay, so there, that's our given. Now, how would we write down our internal energy computation? Our internal energy computation is quite straightforward. We just have to plug and play. So delta E, delta E would be equal to negative 100 joules plus our work, and our work is negative P times the change in volume. So we'd have negative 2 times the change in volume. So that's final minus initial. Delta is always final minus initial. So minus 0.5. Oh, not minus, sorry. 0.5 minus 1. This is equal to negative 100 plus negative 2 times negative 0.5. This is negative 100 plus 1. So our total energy change would end up being oh, sorry, it's not yet the total energy change, because there is a conversion factor for this side here. But basically, it's going to be negative 100 plus 1 liter atmosphere. Now, 1 liter atmosphere is equal to 101.3 joules. Oh, oops. 0.3 joules. So, hold on. This is getting kind of messy. But basically, okay. So we just have to convert 1 liter atmosphere to this. But since it's just 1, we can keep it simple. To be negative 100 plus 101.3 joules. And that gives us with a grand energy change of 1.3 joules. Now, that means that our final energy would be 500 joules plus 1.3, which is just 501.3 joules. And that's an example using the other formula for work, particularly when involving gases. So yeah, I hope that sums up the first law of thermodynamics for you all pretty well. I know that the second half, the one about the gases, it might seem a little confusing, because the visualization of the formula might be like, how did we get here? It's like it kind of just appears maybe, but hopefully my explanation of why we use P or pressure times the volume makes sense, right? And don't forget that whenever you get liter atmosphere, using that formula, you have to convert using the conversion factor. 1 liter atmosphere is equal to 101.3 joules. So yeah, that's all for this video, and I hope everyone learned something today. Thank you everyone for watching, and I'll see you guys in the next video, which is going to be about bond energy and enthalpy. So thank you everyone, and goodbye.